So our speaker today is Mr. Mike Rice, and he is Corporate Vice President of Engineering in the Semiconductor Products Group at Applied Materials. Mike is a graduate of another CSU, not San Jose State. He earned his Bachelor of Science degree in Mechanical Engineering from Cal Poly San Luis Obispo. And then he joined Applied Materials in 1992. So he and I are about the same age. I think I graduated in 1991 as an engineering manager, and he started in dielectric etch. And then he has served in roles with increasing responsibility across etch and foundation engineering, most recently as general manager of foundation engineering. In July 2011, he was awarded the honorary designation of Applied Materials Fellow for his outstanding technical contributions. And before joining Applied Materials, he led new product development for Silicon Valley Group's photolithography tech division. Mike is an idea person, so he holds more than 180 patents across plasma etching, ALD products, robotics, mainframes, and platform architecture. So I'll turn things over to Mike.
Thank you.
You're welcome.
Thank you very much. It's great to be here. And by the way, the size of the group is exciting because you can ask questions all the way along. You can make this as interactive. If something you see makes sense to you or doesn't make sense, just jump in there. I've got quite a few slides, which I'm notorious to have, but I also will go through them fairly quickly. I'll just start with my 3 slides of trivia that kind of lead into the messages I want to get by. But there's a very famous guy who said, I think there's a world market for maybe 5 computers. Anybody have a guess who that might be? Five computers. So this is a famous guy at IBM. Now this is all the way back to 1943. But this is Thomas Watson. You've heard about the supercomputer Watson. It's all named after him, one of the people investing in computers. So he thought the world demand for a computer might be 5 of them. A few years later, there's another famous guy who said there's no reason why anyone would want a computer in their home. Left at home, or in your pocket, or in your car, or anywhere. Another pretty famous person.
Maybe we have people take a copy?
No, too late. You may get the next one. So you may not know. So digital equipment was the market leader in what was called mainframes. These were computers that could be connected to multiple monitors throughout a company, a big company, so they could keep track of inventory and do other things. So he was completely against a thing called a PC. He didn't know why anybody would ever want a PC. The mini computers are more powerful. They're the right things for corporations, and no one would ever want a computer at home. So that company's gone, and he's not around. Okay, you guys might get this one. Who said 64K ought to be enough for anybody?
Mike Rice?
No. No, I don't make predictions like this. This is Bill Gates, and this is back in '81. So it's still what 46, 47, before you guys are born. But these 3 guys are foundational in the industry. But it kind of shows what they thought was going to happen with these things that they were working on. And what they didn't know, and we all know, is it doesn't matter where you go. You can be at a football game, you can be anywhere. Everybody's connected and getting information and watching videos and everything else. So it's changed the world so much more than anybody thought. So I found this photo the other day. It's a picture of a photo. You can even see the reflection coming off the thing. This is me in. This is probably 1987, and yeah, I'll talk about it a little bit more, but a little bit about my background. So you guys are all becoming great engineers. You're investing in yourself. You're investing in your minds. You've got decisions to make when you go into work and everything else. What industry and so forth. I was born in California. One of the few people at Applied Materials. There's not a ton of them. I went to school at Cal Poly. And decided I want to stay in California. I'd like to get a job in California. So in 1985, when I retired, I was 92 at Applied Materials, 7 years earlier at Silicon Valley Group. Anyway, what industry is a mechanical engineer going to go into in California? And I started saying, okay, well, semiconductors is going to grow, but you got to be a chemical engineer or an electrical engineer. What's a mechanical? Oh, equipment. So I looked up equipment companies, and Applied Materials, where I work now, is the world's largest equipment supplier. We do almost $30 billion a year of equipment and services to support the tools and ship new tools out there. But anyway, yeah, grew up in California. That's what I looked like, and I will point out one more thing here, because I used this slide once before. D-size blueprints, and I look at my desk and I kind of laugh, right? So these are blueprints of drawings. This, I can't remember what it was, I can't see it. This was a cross-section of something that I was working on, and these are mechanical pencils. So there was no computer. You had a drafting board with vellum on it. You took a pencil as a mechanical engineer and you drew all the views of parts and you dimensioned everything, and then you had to design all the parts to go with all the other parts and come together and form your assembly. But that's where I started, back in that time period. Okay, so we'll go a little bit further now. When I got there, in production was about 1.5 micron geometry, 1.5 micron. And I'd been there for a couple of years, and my supervisor, who's one of my mentors, he came to me and he goes, Mike, it's really, really great to have you here at Silicon Valley Group. He goes, but I'm so sorry you missed the ramp of semiconductors. And I'm sitting here, I'm 2 years out of school, I'm designing parts for these equipment. I'm like, are you telling me the industry's over? Yeah, it's pretty much mature now, because we all know you can't print smaller than about a micron. And I'm like, okay, well, we're at 1.4, 1.5, so we're almost there. The equipment we're shipping now is for 1 micron, and it was going to be sub 1 micron, we were hoping. But they were talking about the wavelength of light, and there's been so many tricks, including changing the wavelength, phase shift masks and so forth. And now we're printing things. This is a log scale. We're printing things that 5 nanometers, 3 nanometers. I don't think so, but in this sort of range. And I'll explain and show a little bit more about how this industry has really changed along the journey. But yeah, this was the first time I was told the industry was dead. Yeah, and by the way, I actually, as I was putting some stuff together yesterday, I actually pulled up a video from Gordon Moore, Moore's Law, and he kept looking at how much more complex and how much smaller and how many more transistors we're getting on there, and he predicted every 18 months that we'd twice as many transistors at half the cost, higher performance, better reliability, all of these sorts of things. He thought it would die at 1 micron. Even Gordon Moore thought it would die at 1 micron. Okay, so I'm going to do this slide. I think puts a little bit of this transformation kind of in scale here for a second. So I work on semiconductors, but Applied Materials also makes the large equipment for making the OLED panels, liquid crystal panels. So we make make the equipment, not all the equipment, but a lot of the equipment for the displays, for phones and everything else. And this one, 20x cost reduction per area, has happened over the last, I forget how many years, 20 years on that. But this is the one I want to talk about. Semiconductor cost reduction, what is that? 100 million times over 40 years. So it's a question. This is the first question, and the quiz at the end. This will be on the quiz at the end. I'm kidding. But in 1974, I know you weren't born. A smartphone, less power than this one. This is a 5-year-old slide. How much money would we have to put together to buy this much computing power in 1974? Understand the question? In 1974, if you bought this much computing power that everybody has in their pants, how much money would it cost?
Could you buy 1.5 million?
Well, it'd be pretty big. How much? 5 million?
1.5
1.5 million, that's a good reasonable start. Anybody else have another question, another answer, another idea? How much? $1 billion.
I said 30 million.
30 million.
And it's okay if I ask another question.
Yes.
Was there a reason why everyone thought the industry would die in 1988 when Micron?
It wasn't 88, it was before 88. 88, sorry. Yeah, 88. It was predominantly by, and even Gordon Moore said this, it was the wavelength of light. And if you're putting a mask, and you need light to move through the mask to expose so that you can pattern and either do your etch or your depth or the combinations, the smart people, the optical people were saying, well, that's it. Light's light. You can't fake the laws of physics. And then we figured out, not we, I wasn't in this side of things, I don't know it that well, but you go to different light sources. I mean, EUV light source now, I don't remember what the wavelength of that is, but it can print extremely small. Now it's extremely expensive. I can tell that story too. But that was it. And then it was really smart optical people figuring out how to get to the next one. How do they get to the next one? But all the way along that journey, 100 nanometers, 50 nanometers, 30 nanometers, 20 nanometers, 10 nanometers, all the way along, there was huge challenges on being able to produce these small features. I'll show you some real small features here in a minute. Okay, back to the question. There was an answer in the room that's the closest answer I have ever heard. They were only off by $9 billion. $10 billion. So, people run around, I got these things, and then my kids have them, and one day I took my son to work, and he's looking at plasma etchers and all these different things. He's like, what's this for now? This is how you make semiconductors, and he goes, that is required for what I have in my pocket? Yeah. So the reason I'm bringing it up, it shows the massive cost reduction and really what it's done. There's the more than $10 billion. This is another way of looking at it back in the mainframe era. Again, I started right in here, and I think that's 50 billion. This is probably $25 billion a year was the entire equipment for the entire world at that time. And it was mostly going into mainframes, then PCs came along, then mobile, so the stuff that we just showed, mostly the phones and all of the more data and all the processing in people's purses and pants and whatever else. Internet of Thing and AI. I'm going to talk a little bit more about AI because it's even though all these inflections and the internet went in and everything else, I think the change with AI is going to be massive. Okay, let's take a little bit of a look at what our equipment's doing and what these great people at TSMC and Intel and others are doing. 300 millimeter wafers, it's about 12 inches is what is the standard for all the state-of-the-art stuff. If you look at a die, this is showing a 10 by 10 millimeter die. That's way too big for this, but they were trying to say, okay, let's just go look at a section of it. This section is 400 nanometers by 400 nanometers. Remember, 1,000 nanometers is a micron. It's 25 microns in 1,000th of an inch. Human hair is about 3 or 4 thousandths of an inch, so it tells you how small that is. And all of this is metal interconnect, and down here where it starts to become so small that you can't see it is where all the transistors are. So 15 layers, some of them even more advanced devices today are more than 15 layers, etc. Okay, this next slide is more interesting. So if you look at the interconnect on a 10 by 10 millimeter logic device, and you take all the copper, most of it's copper, there's some moly and tungsten down at the bottom metals, and you add it together and you stretch it, it's 95 kilometers long. So in something this size, there's 95 kilometers of metal if you stack them all up and put them in a line. just trying to give you perspective in how small this stuff is and kind of how difficult it is. When you look at the transistor, and we're going to look at it in a little bit more detail, about 11 billion transistors in that 10 by 10, and they all have to work. It's a logic device. If one doesn't work, you throw it away. I could speculate about the latest NVIDIA chip and talk about what that yield might be and the challenges there, but yeah, that can't be more than 20 or 30% yield. It means the vast majority of them don't make it off the line because of the complexity of what we're trying to do. 500 transistors in the width of a human hair, it kind of is the same thing, 25 different materials, more than 100 combinations of the materials. Yeah, so there'll be a question on this one too. So manufacturing steps. There's more than 2,000 steps, so it takes 2,000 machines, or 2,000, it can go through the same machine several times, but 2,000 steps to basically do your etching, do your filling, do your planarization, cleaning, etc., all the way through this thing to go just do the interconnects all the way down to the transistors. And the transistors, this is a gate-all-around transistor, and we're going to watch it. We're going to watch some steps over here. There's more than 500 steps in building those transistors down in those lower layers. Now, this goes really fast. I'm going to ask everybody to count how many different steps happened on this structure. You'll start to see it here. You're seeing etching, you're seeing filling, you're seeing, many different steps. And this was built up to kind of give perspective in all the things that are happening to try to build such a thing. I don't know if it's 500 steps. I keep laughing. You can't. I'm sure it wasn't, but just give you an idea of the complexity, what it takes to put down the metal, take out the metal you don't want, fill it with dielectrics and other materials. I'm going to show you a little bit more detail, but very, very complex. I like this one a little better. It'll zoom in here for a second. It'll stop. Okay, so this is gate-all-around. Obviously, it's a model of leading-edge transistor technology, and there's 10 nanometers between these two gates. Those things you're seeing are representative of the molecule size. And in 10 nanometers, this is 100 angstroms. Silicon dioxide molecule is about 2.7 angstroms. So if it was 3 angstroms and it's 100 angstroms, you get about 30 molecules. That's it. So you start counting these layers. There's 5 different materials, and then 5 more coming out here. These things are 1 or 2 nanometers thick. So you're talking about 10 to 20 angstroms where if it's a silicon dioxide, there's only 3 or 4 layers of that in the device. And when we talk about Moore's law and scaling, and we talked about litho a little bit, not only is it challenging to print the smallest features, but when you start talking about putting 2 atomic layers down, and okay, you want to shrink it to the next node, and you want to go to 1 atomic layer, you start getting to where you can have pinholes, any defect in this lattice, and your device is dead. So we're really pushing the absolute limits of molecular physics. Periodic table. So these were the first gases and materials. What does this show? Before 1990. These are materials that were added from 1990 to 2000, 2006 to 2020, and this is what we believe will be added. So if you look at the periodic table of the different elements that are used, in the chip industry, it's starting to get to what, more than 50% of all the known elements have a place in the semiconductor manufacturing and devices. And that leads to, okay, a little bit about equipment. So not all those materials can be put down the same way. Some of them like if you're depositing, you can ALD deposit them atomic layers, so one atomic layer at a time. Some you can use CVD. Some CVDs need plasma. Some CVDs can be done thermally, chemical vapor deposition. Epitaxy is growing predominantly silicon germanium, lattices and structures. Those are done at higher temperatures, but the temperatures are actually dropping. They used to be done at 700-ish, 800. Now we're dropping down below 450. We're getting down to where we need other sources of energy to form the crystal structures. Metal deposition, CVD or PVD. I would have thought PVD was in here separate, but it's not. PVD, we basically put targets in and we hit it with argon, and we sputter materials down. It comes raining down on the wafer and coats the wafer. Plating is electroplating. Selective deposition, materials that will deposit on some things but not other things, so we can do bottom-up fill and so forth. But there's lots, every one of those different lines is a different tool type in order to be able to put down all those different films that we were talking about. And then shaping and patterning, you got to be able to etch the materials, whether they're metals or dielectrics. You got to be able to planarize. We do polishing, which when polishing came out and it's a slurry and it's dirty, you were like, how the hell are we going to ever get the wafer clean? How are we going to be able to yield anything? And IBM really did a lot of that front work on figuring that. But we polish materials like copper. Copper is the majority of the interconnect that you saw. When you put that down, you can't really etch copper. It's not easy to etch copper. So what you do is you polish it off with a slurry, and then you go through all the cleaning techniques. Selective material, these are gas phase, typically radical sources for removing materials. Pattern shaping, we have equipment that creates an ion beam, and we can take the wafer and tilt it any direction, and we can actually elongate features or change the shape of features, meaning that what you've etched. Modify implant is, what do you want to implant at high energy into the material. Thermal processing, treatments for removing organics and oxides. And there's also stuff for oxidizing stuff. We have a measurement division. We do a lot of inspection. KLA Tencor is another company that's in this valley that does a lot of the inspection. They're actually the leader in inspection. And then these are kind of core things used to make the devices, but there's also a big push on packaging. And packaging these devices really has been overlooked for the last 50 years, because if you stayed on Moore's Law and you just made faster, smaller transistors, cheaper transistors, you'd have a great market. If you took your eye off the ball and started messing around with how am I going to package my microprocessor with a memory, with this and with that, if you fell off Moore's Law, you get yourself in some serious trouble. Today, Moore's Law is, I would say it's dead. You're not going to get scaling, where it was just scaling all the way along that curve. What you're getting now is different materials. You're getting 3D structures, 3D NAND. The thing that's in your computers and in your phone. It used to be hard drives. Hard drives are slower. They're not very reliable, et cetera, et cetera. So 3D enabled the cost to be in play and capacity to go up. 3D DRAMs are coming. I think they're going to make it, so to be able to make DRAM vertically as opposed to just in a plane. So more 3D is coming, as well as how do you package these together. But all I'm trying to say is there's a lot of different technologies, mechanical engineer wonderland in these things. This is one of our, maybe the most famous tools in the industry. This is an Endura, and this has been used for many, many years, probably invented in 1990, and obviously it's a bigger version now. That was on 6-inch wafers or 5-inch wafers. But the way the tool basically works is these are called FOUPs. And I remember being in the car with my kids when they were young, and I'm doing conference calls, and I'm talking about FOUPs, and then I'd hang up, and they'd just start laughing. Dad, what's a FOUP? So it's a front opening unified pot. So it's basically the wafers are in an ultra clean environment here, and there's a door on the front that gets taken off. This is an ultra clean environment as well. ISO class 1. You think about hospitals being clean. That's clean. You can put a wafer in there for 24 hours, take it out, and measure pre and post on the particles. You will not find one adder on the wafer over an hour. You put it in here for 10 seconds, and you take it out. This is class 10 million or something. That's class 0. There's really nothing in there. So this wafers come out, go in here. There's robotics that put them into load locks. Most of our tools are vacuum tools. The load locks pump the volume down. Now the wafer's in vacuum. They'll go into these chambers. I'll show you a few more about these, but we can do pre-clean. We can do ALD, CVD, PVD, many different technologies. So we build these tools in many different ways. So there's vacuum robots in there. These are PVD chambers. This is an active pre-clean. Gas systems are typically down below, as it's showing over here. Power goes in to form plasmas, etc. But it just gives you an idea of what a tool might look like. That's a $10 million tool. Can be more to be able to do these leading devices. Okay. Another challenge we've got is we looked at gate all around on the other, and we talked about 10 nanometers in here and how difficult this is. So we have to do this not on one transistor, but on every transistor in a die. And then we've got to do it uniformly across the whole wafer. And then we've got to do it on 100,000 wafers a month, and multiple times on the 100,000. Remember, there's 3,000 steps when you start adding these things up. So they go through these tools many times. And then we've got to do that in multiple fabs, in multiple countries. We have to be able to match it. So the complexity of trying to control that environment is extremely difficult. And we spend a lot of time on matching and control and sensors. And how do we know if something's drifting? So anyway, that's the complexity of manufacturing at scale.
Can I ask a question, Mike?
Of course.
I can understand, especially when you think about fab scale. Could you talk about the complexities? You and I have talked a lot about internationalization and how important it is to think about working in different countries, of trying to manage that last final scale when you're trying to go to all your fabs across maybe different countries and different issues there, what those issues are.
So yeah, like Intel's got 5 leading fab areas. Most of them are in the U.S., but they're also in Israel and so forth. TSMC, Samsung's predominantly all in Korea. TSMC is predominantly in Taiwan. They're building a fab here, but they work out their recipes for every single step and how they're going to measure everything on every single step. And they teach their operators and their management inside the fabs, what to look for. When they buy a tool from Applied Materials, like the one I just showed, if they want ALD process at 10 nanometers in 20 minutes, it's got to be 10 nanometers in 20 minutes. In fact, it won't be. It'll be an angstrom. They'll come back and they'll say it's 98 angstrom, plus or minus an angstrom, and that means we've got to be able to measure and control our power, the temperature, the pressure, all the gases that are going in. Every single thing has to be controlled extremely precisely. So we have procedures. A lot of it is in the software, because as much as I love humans, there's variation in humans. You tell 10 humans to go do the same thing or give them the same procedure, and you go watch it. It's like Laurel and Hardy. It's an old, it's Three Stooges, right? It's very hard to do it without sensors and software constantly monitoring and checking things. So we do most of it through that. Our customers predominantly all speak English, no matter where they are. It'll be their second language if it's Japan, Korea, Taiwan. But these are smart people. They're well trained, and we communicate predominantly in English. We have account teams out there that can translate if we need to, but most everything in the industry is done through English. Like all the displays, when you go look at the monitor, it's always in English. Doesn't matter where it is. I'm not sure that helped or not.
Yeah.
What are some of the most common challenges that you may face when you do a manufacturing site in another country? Like how do you overall control the risk levels of that?
So our manufacturing facilities, we only have two. One in the U.S., which is in Austin, Texas, and the other one is in Singapore. And we use the same procedures. We use the same test equipment in both. In manufacturing, you'll hook these chambers up to a computer. We'll run pressure control systems. We'll run all the MFCs, mass flow controllers. We will go check everything through automation, and it'll come back with a report as to is everything okay or not. When we go and ship it, so we have to pass everything to start with. Then we go ship it, and it gets installed at a customer site. We do the same thing. We go back through the same thing, because now it's been in a crate, it's gone in an airplane, it gets installed and so forth. But that's the starting piece. Now that tool's going to keep working for probably 20 years. And like an etch chamber, you open it about every 3 weeks. The reason you open it every 3 weeks is it eats itself. Because you're running halides, fluorine, chlorine, bromine, and there's materials in there that when they get etched, they have to go to gas phase. So they have to be ultra pure materials, but they do get etched, so they go away. As they go away, we got to go in, clean up, replace the parts, bring the chamber back online, check everything, and we've got to do it every 3 weeks. And by the way, I would say 75% of the time when we check the chambers today, it passes. 25% it doesn't. Particles are high. Edge uniformity is a little off. Etch rate's off. Something's off. And our customers, when they go through a requal for etch, they spend about $10,000 in test wafers just to try to requal a chamber. And they'll do it every 3 weeks. Huge number. And these section heads, these senior people in these fabs. So if let's say you're doing metal, metal 1, 2, 3. So the first layer is of metal. You're doing the etch, and you're an etch person. You've got 120 chambers on 40 tools, and they're running in production, and they're constantly going down for I got to swap these parts. I got a particle problem over here, so constantly going down, and the fabs run 24/7, 365. You do not shut off for Christmas. You do not shut off for anything, because when you shut down, when you bring it back up, you go back through a major recall to make sure everything is okay. So it's these poor guys and gals. They get I got to get that chamber back online, because if we don't get the chamber back online, I'm going to have WIP, work in process, piling up, and the fab manager is going to get on me, because if I don't get this down to the next steps, we're going to have shortages on shipments coming off the end of the line. And then they get a call during the middle of the night, and there were 10 wafers run, and 9 of them passed. What do you want to do? Well, which one didn't pass? Particles were high. How high were they? 3 adders. Okay, run another dry clean, one more test, call me back in an hour. Okay, now we're down at 2 hours, two particles, but the whips, okay, put it in production. Then you find out, you know, your yield on those wafers that came out of that for the next few days. Well, they'll know this, you know, hours later or days later. Yeah, we lost $1 million in wafers. So the challenge of running these things in production, because these process windows are so small, and what we're trying to do with these are so tight. When I tell my friends that, yeah, you know, our equipment's not very good, they go, I thought you guys were the leaders. Yeah, our competitors are worse. But it's not very good. You know, if you're buying a lathe or a CNC mill, you expect it to be at 99.999% of the time, and it doesn't need maintenance every week. You wouldn't buy such as that car. If I told you your car is going to go down for scheduled or unscheduled maintenance every 3 weeks, you'd say, I'm not buying that car.
No.
The problem is the other supplier, they may go down every 2 weeks instead of every 3 weeks. So it's very complex. This is good news because it's why I get excited about the equipment, because if I can move that from 3 weeks to 4 weeks at $10,000 every time they do a wet clean recovery, I just saved a bunch of money and made the products better so that we can get more of that market share, so that the families that benefit from working at Applied Materials, they get, you know, their bonuses at the end of the year and all that stuff. So there's I don't know, 50 years of improvement that can happen on these equipment. Yeah.
What is the current yield rate on current gen wafers?
Well, I don't know exactly, but I'll give you my speculation on one, because it's interesting. So you ever heard of this company called NVIDIA? So Jensen, I've talked to Jensen 6 times. I mean, he's amazing. He's really, really, really amazing. But I remember the second meeting we had with him, he said, you know, I have to tell you something. He goes, I don't listen to my customers. And I go, what do you mean? He goes, well, customers kind of know what they want, but they don't know what's possible. They only know what kind of is. So they know really clearly kind of what is, but they don't necessarily, because they have a lot of expertise in what they're doing, but they may not have expertise in other areas. So Jensen made the biggest chip possible. It's like this big. It's full field on the light sources for exposure. You can't really make a bigger chip. And when you make a bigger chip, what happens to the yield? Yeah, it goes down, right? If they're really small and there's lots of them, yeah, you get 10 particles on a wafer, those 10 are gone. But if you've got one die on a wafer and there's 10 particles in a wafer, the yield's 0, because you have to get them all. So these chips that he's got on the next gen, you know, GPU for AI, he published the size of it, and I got AutoCAD out and I started laying them out on the wafer. 22 of them fit. 22 of them fit on a wafer. Okay.
Wafer size was
300
millimeter wafer.
Okay.
22. Okay, and then I looked at those and I go, I don't think you can yield half. Kind of no way you yield half. But let's say he yields a quarter, so about 6. Okay, he says he's going to sell them for $40,000 each. So every wafer that goes through the tool has a street value of $250,000. They run through our tools, slow tools, 20 wafers an hour, fast tools, 100 wafers an hour, call it 50. 50 wafers an hour are going through the tool for that. That's the most expensive wafer there is, so I grant that it's not a DRAM, but you multiply it out, how much money is really running through there, and how much stress there is on the people that are trying to make those chips and yield those chips, and you know, it's just unbelievable. So I don't know the exact yields, by the way. The customers always tell us we need the price down and we need the throughput up. And that's not really the way they buy. The way they buy is whatever is going to have the highest yield. that's how they keep their jobs, that's how they really make their money. But the easy thing to hear from a customer, they're always gonna tell you faster and cheaper. If they come to you and say, oh, your tool's really great, you know, you've increased end-of-line yield by 1%. Then I go, okay, I know TSMC sells their wafers for $30,000 each. 1% is $300. $300. If it goes to our tool at 100 wafers an hour, that's $30,000 an hour. 20 hours a day, it's up. That's $600,000 a day. We sell the tool for $10 million. They make $600,000 a day more if we can out yield 1% end of line. So they don't want to tell us. We only know because do they buy our tool or not buy our tool? And they don't buy the cheapest tools. Does it kind of make sense? But we don't really know. They know the yield. Okay, I got to move faster. A challenge. So this is back to gate all around, but things are getting smaller still, and I'm going to pick on this metal interconnect here just for a second. You know, to put that to build that metal interconnect, there's this number of steps. And I'm kind of highlighting, you know, these steps that we looked at for, you know, for these you know, interconnects at the transistor. Resistance, contact resistance, and total resistance of the line is a big deal because, has anybody heard there's a power problem on you know, state-of-the-art chips? Every time you switch those transistors, it takes electricity. It is a big deal. So anything we can do to reduce line resistance reduces the energy required, and it's a big deal. So this is an example of kind of the things that we do. We build tools kind of in three different kind of categories. One is this is the one you saw before. We can put the same chamber around here, and when the FOUP shows up, the 25 wafers, first one goes here, second one goes there, and we do it in parallel. We call this unit processing. We also do things where if we've got two tools, we'll communicate between the tools and we'll coordinate what's happening in one with what's happening in the other one to produce a better result. The other one we do is we take some of these chambers and some of these chambers and some of these chambers, and we can connect them through this vacuum mainframe into, we call it IMS. It's an integrated process solution, and I'm just going to give an example of why this is important, and it's more important all the time. So again, this step of the sequence, I'm going to start by going after, we're going to start by going after these two here for a second. I'm going to give an example of this etch followed by the epi growth. So the problem is via resistance, and as you go to smaller nodes and the geometry gets smaller, the resistance of the line gets greater. We all know that. But every time this goes up, that means more power, and that's one of the big challenges we've got is to keep the resistance down. So the interface is what I'm going to talk about here on this tool. It's a resistance between this metal, this copper, and this copper, that interface. So here's a case where we did the etch for cleaning the surface perfectly, followed by epi growth. And the epi is, if you do the cleaning in a separate tool, and then you bring the wafer through air, I mean, we love air, right? It's good for us. We breathe it, it's got oxygen, we need it, 21% oxygen. It's got carbon in it, it's got water in it, it's got metals in it, it's got a bunch of stuff in it. When you start talking about one atomic layer in the transistor, every atomic layer matters. You can't expose, in between those layers, you can't expose it to air. It oxidizes, it corrodes, and it deposits stuff. So what we do is we start integrating these steps together on the same tool. Because this is very high vacuum, there's no impurity in here. There's no particles or impurity in here. Wafers go in, we pre-clean it, then we'll go run our epi. And when we do that, we start to get contact resistance, significantly better. The tool's more expensive, but the contact resistance goes down. The reason the tool's more expensive is If this is down, the whole thing's down. If that's down, half the throughput's gone. When they're separate tools, if this is down, doesn't matter. You go through another one and you bring it back in. So this increases the cost, but it significantly improves the performance. And I like this one better. This is, we went after another series there. I won't go through too much detail, but you'll see the wafer going through all these different chambers in order to put down the metals that we want. And while the wafer is going through, these different chambers, it's going to tell you what's being done. That's the cleaning, surface prep, and you'll start to see what it's doing inside the features. So that's an ALD process, atomic layers being put down on the side of the feature. This is metrology. We're measuring the thickness to make sure we've got that right. I don't remember what that treatment is. This is the liner deposition. Liner is to make sure that the metal stays where it's supposed to be and doesn't diffuse through the dielectric. Liner deposition. This is copper, and then copper reflow, and we'll do it twice. And then that wafer will reflow it again. Yeah, and then the wafer will come back out of the system, and all the wafers will go through that sequence on this again. We're just trying to get really pure interfaces because things are so small, and it makes a huge difference. And that particular one, you can see on the right, instead of the predicted via resistance going up, we were able to hold it flat over the node because of the purity of what we were able to deposit. Last kind of slide. This one, I won't go in details, but I kind of said it. It used to be Moore's law, scaling, 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 scaling. Didn't matter, just scale. Can't do that, anymore. So now the transistor structures, gate all around, a completely different three-dimensional transistor structure that adds value. This is backside power. So transistors now, we're putting interconnect on the backside as well as from the top side. Gives us more room so we can make things a little bit smaller. Advanced packaging is a big deal. Memory chips, logic chips, tightly coupled so that the speed of getting data in and out is much faster than it is if they're far apart and separated in PC boards. Memory, high bandwidth memory and different memory structures. 3D DRAM, very hard, very, very hard, but I'm convinced that's going to happen. And then we're doing work on silicon carbide and GaN for power devices. This is for electrification of the planet. Cars and your solar and everything else. You need high performance power devices. So there's going to be a bunch of innovation in all these areas going on for the next, I don't know when it would ever stop. Applied Materials is investing, I think I said $5 billion, I'm not sure I'm supposed to, but it's a number in that ballpark. It's a big number. The reason this building is over here on Tasman and what's the parkway called? Central Expressway. So if you see the big cranes out there, that's us building this building. This is for research for us and our customers to come together and research to solve those problems that we just talked about, all those opportunities. This is the current facility we have there, this one back here. You've been in the Maidan Center, I think, right?
Yeah.
And it looks small. It's massive. This is, I don't know what that is. It's 150 yards long and 75 yards wide and 6 stories tall. There's only one level for the equipment. And going back to the beginning, we all know, where we are today, but I do want to, I don't know, I'm encouraged, I'm scared, I'm happy. AI is coming, and we've been talking about AI for, 30 years. But remember I said this thing was $10 billion, 40 years ago? Can't run AI on something like, you can't run AI on something like, even this you can't. you need extremely high speeds, and data in and out, and it's gonna take a bunch of computing. I'm hearing massive numbers of investments by big companies to get their AI engines and all the computing power necessary to go do that together. But I think it's already starting to change things, but I consider it the second pitch of the first inning. So it's very, very, very new, but it's gonna be extremely powerful. And I think it's gonna be the biggest inflection in my life and maybe all of our lives. So just a prediction. Okay, summary. Semiconductor industry has changed our lives, way more than we ever thought. And I gave you 3 of the founders who were off by orders and orders and orders of magnitude. Again, down here at the bottom, I was told in 1988, it's mature, it's done, whatever. It's crazy how far this is advanced. And as an engineer, I figured I'd put one slide down just with some comments. First of all, engineering and technology, because I've been very close to technology as well for many, many years. Great field, learn to solve problems, which is so valuable in everything. Great opportunities that will await each of you in this. All I can say is master the fundamentals and the first principles. Sometimes people get worried about, someone's cheating on a test or something because they're using AI. I can tell you, if you don't understand them in the real world, that's where the test really happens. So, make sure you understand those first principles and the fundamentals of your disciplines. Those fundamentals, they'll be a tailwind for your whole life. It's like on your bike in a race and you've got 20-mile-an-hour wind behind you because you've got those principles mastered. Remain curious and strive. I talk about this, strive for what is possible and not what is normal. It's a trap. A lot of times I go in and look at problems and the team is really, really smart and they're trying to solve it and they can't seem to get out of, this is the way it's been for 20 years. But if you can really step back and say, don't even think about how it's been done. Go back to the first principles. What is this problem? How are the different ways you can solve it? But really try to think as big as you can about what's possible and watch out for the trap for falling into just doing what's normal. You're becoming leaders for innovation and execution, and I believe you'll be the next group of people changing the world. That's kind of it.
Great. Yeah, all right, we've got the room till 1, so if folks have some questions, haven't already asked them yet, let's have some questions.
Give like an idea of so you're talking about like an angstrom of precision. How do we get to that precision?
50 years. No, seriously. We work like crazy trying to make our tools more uniform, more precise, more in control, and new techniques show up as well. For example, atomic layer deposition. I did an atomic layer deposition tool about 4 years ago, and now it's shipping for the most advanced low temp silicon nitride. It really does put down each atomic layer very precisely. If you want 12 atomic layers, we can give you 12. If you want 14, we'll give you 14. Without that ALD process, and if we were trying to do it with CVD, where you just put 2 gases and it just deposits out, the non-uniformities across the wafer are higher, the variation's much larger. But if you basically put in a precursor, which coats monolayer on the surface, and then you convert it with nitrogen to silicon nitride, then you put another monolayer, and then you convert it, and then another monolayer. It's not a CVD reaction, it's an atomic layer reaction. That's an example of how to get to atomic layer precision. The stuff I showed, 2 atomic, 3 atomic, you couldn't do that CVD. 20 years ago, you couldn't. We wouldn't have equipment. We wouldn't have known how to do it. So you keep working that stuff. I don't know how they're EUV lithography. I forget what the wavelength is. It's basically a laser of extremely high power, hitting BBs of tin. So tin's firing across this chamber, and they're pulsing lasers to basically make a plasma out of it, ionize it. Tin, when it vaporizes, has a very short wavelength, and that's what you need to print these smallest features. That tool is $150 million each. It's got significant downtime and maintenance time. It runs, I don't know, 30 wafers an hour. The immersion tools, the next state of the art behind that was 150 wafers an hour, $30 million, and just uptime's much, much higher. So, and if I showed you the tool, the tool fits kind of in this size of a room. And the tool's a little bit smaller, but then you say, well, where's the power coming from? Oh, you mean the lasers? Oh, they take you downstairs, and it's the other half of this room, and I don't know what the efficiency of it is, but I think something like 1% of the power that's put in goes to photon energy. 99% of the laser power is just absorbed in other things to be able to get there. So it's when you look at it, it's just, as a mechanical engineer, I'm going, this is just amazing, you know, that it works at all. But that's what perseverance is around, you know, this sort of technology. So that's another one. You couldn't get there without these. The other exposure source I'm talking about is the light travels through liquid. Because if you travel it through air, I forget what happens. You probably even know better, but what is it? The refractive index of
Well, no, air is like the least. So I did see something about lensing with simple water molecules or oil.
This is it's complete. It's a complete liquid between the source and the wafer, and you know that was another one that came out 15 years ago, and it took us, you know, another 10 years before EUV finally came out. EUV was at least 10 years late to market because it's just that hard of a technology. Maybe I can answer that. There was lots of questions.
Question here, question here.
In terms of the slide you have with the periodic table showing how new elements are being added to the semiconductor process, what makes a certain atom helpful or unhelpful? Like what gaps are these new ones filling?
So the good news is I'm a mechanical engineer, so I can kind of go, yeah, I'm not really sure. You know, like for example, you think we used to use aluminum for the interconnect, and it got beat badly by this copper, which makes sense. Copper's a good conductor, and we learned how to make it with large grain size because that helps with the lowering the resistivity of the material. Now there's moly. There's a lot of work to go to moly, and I'm like, moly as a good conductor. There's a reason, and I don't exactly know the physics behind why moly is a better conductor than copper, but it's starting to work its way into the most advanced devices at the smallest features. So I'm not a chemist. I can tell you, oh yeah, well that's our copper deposition tool, and this is this and this is this, but I don't know the physics behind exactly why all those materials are there.
Did you have a question?
Yeah. So for the part where you talk about the, I think it was co-optimized unit processes. So like, when you put like the unit process together, is there sort of like a program where like you use to like control the processes, or like do you have to, like, does your company create those programs, or do you have to outsource from like another?
Yes. Yes to both. So we like solutions. So if there's somebody that can help us, you know, through an algorithm or a sensor or something, we will definitely work with many suppliers to go get stuff done. In general, all the real-time control of all the recipes, all that's done by us in our tools. And because we also have metrology, we can measure, for example, we etch the wafers before epi is grown for the transistors. And if our etch uniformity is 5%, it has some shape. We're not perfect. It's a plasma etcher. So if the CDs, the dimensions of the features are a little, let's say, smaller in the middle, and then they get a little bigger, and then they're a little smaller at the edge, if we know that that's what we did to that wafer, that information can feed forward to our epi tool. And our epi tool can try to counteract that, to put down the right amount of epi in the different size CDs to try to optimize the transistor speeds, for example. Usually it's a non-uniformity in one that when it's understood by the other one can do some amount of correction for the incoming non-uniformity. And then if it gets to interface where I can't afford any copper oxide is not a good conductor. I gotta remove the copper oxide, or whatever. Any of these contaminants from air, that's when we wanna put it in under the high vacuum, do whatever cleaning treatments that we need to do to recover the surface. Then we go put the new layers down so we can get a very pristine contact or barrier or whatever we're trying to do.
For that last step with the copper deposition, are you guys actually doing like a gaseous deposition, or is it more like a film and then you're heat treating it?
I missed the beginning of that.
So that the last step in you guys' machines, you're adding two-stage copper layer to it.
Yeah.
Are you guys doing it with like a gas deposition, or is it
So
like a film?
the copper we sputter. If it's small, so electroplating is another way to put down copper. When the features are large for the copper, what we do is we put down a barrier, because copper will diffuse through the oxide layer, so we put down a barrier, then we'll sputter copper, so that's a conformal film, fairly thin. But because if you wanted to sputter it to fill, which we could do, it would take a long time. It gets taken out, it goes to electroplating. When you get down to really small features, then you don't need to do the electroplating anymore. And what you saw there is the smallest ones. We'll sputter, and then we'll reflow it, and then we'll sputter it again and reflow it again, and now we've got it filled.
So in that stage, you guys actually have like a heat treatment element?
Yeah.
Nice.
Yeah. In ultra, I mean, obviously it has to also be absolutely zero.
Yeah,
Zero
otherwise it would
oxygen.
oxidize.
Yeah.
Um,
Yeah. There's all kinds of tricks.
Are you, sorry, give me one moment. The silicone wafers that you guys, are you guys essentially fabricating your own silicone, like crystals, or are you buying those?
We buy them.
Okay.
We sell the equipment that puts the silicon epitaxy on
Onto the
top,
wafers,
on top of those wafers. But those are Tucholsky pulled single
Yeah.
crystals, sliced and then polished, and it's predominantly done out of Japan. There's a couple good suppliers over there. They're crazy. They're about $70 each, 300 millimeter.
Wow.
It's amazing how cheap it is.
Yeah, no, the value add from your starting material to, what did you say, $250,000 a wafer?
Well, that's the street. So TSMC,
Wait,
I
like
think
street
sells them
price?
for $30,000, and then Nvidia and Apple and everybody that's getting those wafers, they're selling them for whatever their street price is.
Yeah.
They can charge for it.
Yeah, we do have if you are a student and you have a class, please feel free to step out. I don't wanna have students held back from the classes, but we've got lots of questions from our students, so this is great.
I have two questions. Could you give us some examples of how AI is being integrated in your machines in order to control those manufacturing processes? And the other question that comes from this question is, since we don't know your fill rate, then how are you not gonna use that information but to optimize your machines?
Yeah, so the first question is, how are we using AI? There's a lot of things we're starting to do, but one of the big ones that we're working on is we run a lot of test wafers, and some of the test wafers can be quite expensive because you have to TEM them to go and get the measurements off of them, and that's a couple $1,000 every time you go do this.
Great, can you, for the acronym help, TEM?
Oh, it's an electron microscope. to be able to get the thicknesses of the films and features, the critical dimensions, et cetera. So it's a measurement tool. So what we haven't done well historically is there's all this data and there's all these wafers coming off of all these tools, and the tools are running and they tell us this is the temperature, this is the pressure, this is the power, this is, and the recipes and so forth, and we know the hardware inside of it. If we had collected all that data, which we are now, you collect all that data, now you can process it because you've got the conditions that it ran on and you've got the metrology results. Now we can start to use AI to predict which recipe would make more sense, which chemistry should we use, what pressure regime should we be in. So large data, being able to look at large data is something that we expect it to be great at. So that's one of the powerful ones that we're working on. But there's a lot of little ones. We use AI in meetings. A meeting like this. It'll just listen to the meeting. You get done and say, can you tell me all the questions that were there? Okay, can you print it in a report? Okay, were there action items? Okay, who has the action items? Boom, done. So there's stuff like that. There's stuff on the mechanical engineering side as well, where there's some tools we're looking at on, we want to minimize the stress, but we can't afford more deflection. And you start talking to it, and it starts coming up with ideas or helping you. What if I made this a little thicker? What if I did this? It's very, very fast at being an assistant to us. So that was, and then that was AI. The other question was
Without using the information of the already, because that's something that you don't know. How are you gonna use AI for that?
no, we can't use AI for data we don't have, but TSMC and Micron and Intel and they can, and they have massive amounts of data, massive amounts of data, and they're looking for why was the yield lower on this one, and they look at all the wafers and all the conditions, and they're doing that. That's their IP, that's their knowledge. You can imagine this battle between Intel and TSMC to be the leaders of logic. That information, how you do it and what's going on and everything else is absolutely critical. So we are very careful with our customers' information. We do not share across, if we're working on something for Intel, we're working on something for Intel, and we firewall that really, really well. But that's their know-how. That's part of their soup on how do they learn faster and yield higher.
Yeah, great. So we got to move to the next event, but I want to